coordinates, okay? The easiest way to get to a large distance is to go in the same distance in all the coordinates at once, right? So you're not fixing all the coordinates and changing one, you're changing all of them at once. That's the fastest way to get to a large distance. So as we'll come back to this later in class, but the L1 distance is going to be less affected by outlier points or outlier coordinates, because if you're moving along one coordinate, it's going to affect it less. Whereas the L infinity distance, the only coordinate that matters is the largest one. The L infinity, the L1 averages over them. It's a perfect average. And the L2 is somewhere in between. It's more affected by outlier coordinates than L1 is, but not as much as the L infinity. All right, so there's one more I had on the list here. So what is the L0 distance? Well, okay, so this is a little...
All the points.
It's what?
Isn't it all the points, because anything to the power 0 is 1?
Well, it's kind of going to be like, you know, L infinity was a little bit weird here. So it's kind of in the limit as this is happening here. So
Yes.
so how you typically would define this is, and you know, this one's a little stranger. It's going to be d minus the so this is my notation for an indicator function. It's 1 if A and B are equal, and it's 0 otherwise. Right? So this is equal to d minus the number of coordinates that are equal to each other.
Yeah.
Okay, so this is sorry. Okay. So what does the L0 ball look like?
It's 5 points. 5 points, one at the center and the other 4 points.
Well, yeah. So this is so any point along here, along the axis, is going to have at least one point that's different. If I have 2 points that are different, say I'm out here, what's the distance from C to the origin under the L0 distance? Right, so the maximum value can be D, because you're D subtracting something here. So yeah, so they're like spikes, right? So this is a distance of 2, because 2 coordinates are different. Any point along the axis is a distance 1, because only 1 coordinate is different. So it's really, I can't even really draw it, but it's really these spikes here. Okay, so let me try and draw something else. Let me draw now I can define this for any value p here. Usually you say that p is greater or equal to 0, or greater than 0, because this is kind of not well defined, and say, because infinity is kind of weird again. So p is greater than 0. So I can define this for L 1/2 distance. What is the pattern here between L infinity, L2, and L1? Where is L 1/2 going to be?
Inside L1.
Yeah, it's going to be, they're shrinking, so it's going to be inside of L1 somehow. Now, it's still going to include these points here, on these axis points. Because even if I took something, there are two coordinates, one of them is 0, so taking it to a power and whatever doesn't do anything. The other one, the distance is 1, I take it to a power 1/2, then I square it again, so I get 1 back. Right? So all the axis points are going to be here. And then something weird is going to happen. It's going to kind of look like this. So this is the L 1/2 unit ball. So this is pretty strange, right? And as P gets smaller and smaller, it gets closer and closer to the origin. It shrinks in. Right? The same thing if I took the L 3/2, it would be in between L1 and L2. And if I took the L3, it'd be in between L2 and L infinity. It would kind of be coming out here. There's this whole spectrum of these LP distances. Okay? So what's important to note, and we'll come back and use this property later in class, and in one of the lectures on regression, is that L1 is the smallest p-value where the unit ball is convex. Okay, so convex means that if I take any 2 points inside and I draw the line between them, right? So let's say I took 2 points inside of the L 1/2 ball and I drew the straight line between them. It goes outside of the ball. That means it's not convex, right? But L1 is the smallest one, which is convex. And so this will be important. At some point, we'll actually want to try and do something that minimizes the L0 distance, but it's really hard to deal with computationally. The L2 turns out to be really easy to deal with, and L1 you can still work with, and it does much better than L2 in certain regards. It's much more robust to noise. And so we'll use the L1 as kind of our approximation of L0, because we can compute with it because it's going to be convex. All right. Okay, so I think this is what I want to say about these LP distances. So we'll come back to these. So yeah, I guess I'll mention, I briefly talked about this on last week, Wednesday, that there's this locality-sensitive hashing technique for the L2 distances, and that involves choosing a random unit vector and projecting all the high-dimensional points onto it using this dot product. And then binning these, and this gives you a locality-sensitive hash. This works for any p-value, I think, larger than 0 and up to the value 2. There's something called a p-stable random variable, and so in particular for L1 distance, you can do this similar thing for locality-sensitive hashing. Using that, you need to pick, the difference is instead of picking a Gaussian random variable, which is going to be symmetric to a random unit vector, you pick a Cauchy random variable, which is going to have more weight along the coordinate axis. So it kind of aligns with the L1 ball. And that's kind of the reason why you need to pick different ways of random variables to get these different hash functions. So we come then to class, maybe I can talk more about that if you're interested, or there's some details in the notes. Okay, so in all of these LP distances are metrics. So they'll all satisfy these metric properties. All right, so the next so just to kind of so we kind of talked about the Jacquard we talked about the Jacquard distance already. This was 1 minus the Jacquard similarity between these 2 points. So this is, say, the Jacquard distance, and this is defined when A and B are sets. Okay, So these work for distances, the Jacquard distance, these work for vectors with real value coordinates. These work for sets. We talked about several other of these distances or these similarities between sets, and you can convert all of them into distances this way. And most of them were actually metrics. Just to remind, the Jacquard distance between sets A and B is equal to 1 minus A intersection B, the size of this over A union B. Okay, so just let's go through and think through these metric properties. The distance is always greater than 0 because this is a ratio where the intersection is always smaller than union, and you're subtracting it from 1, so it can never be larger than 1. The distance is symmetric because the operations of the intersection and the union are also, the size of these are also symmetric. So it's, if A and B are equal to each other, then I should have a distance that's equal to 0. That's going to be because the intersection is going to be the same as the union. So this ratio is 1, 1 minus 1 is 0. If they're not equal to each other, then the union will contain something that's not in the intersection. So this ratio will be strictly smaller than 1. And so this cannot be 0 unless they're equal to each other. The triangle inequality is a little trickier to see. I can go through it, but I think I'll spend more time on the other sorts of distances. There's a proof for it in the notes. It's not too hard to see. Okay, so any lingering questions on this Jacquard distance? Okay, so another alternative to the LP distances is what's called the cosine distance. And so this will again be defined on A and B where they're in RD. So that means that these are these vectors. Okay, and the cosine distance now is being defined as 1 minus the dot product between A and B divided by the norm of A times the norm of B. And so if I'm writing this norm notation like I did here, and I admit the p-value, implicitly that means p is equal to 2. Right? So this is the 2 norm here. Okay, so what does this distance mean? So do you want to know why this is called the cosine distance?
It is cosine of two vectors, right? A projection of one over the other. Projection of one vector over the other.
Yeah, so but why is it called the cosine distance?
Because you can write it as a modulus of A and B cos theta. Theta is the angle between them.
Yeah, so let's say that, now I'm going to think of these now as I've got this vector space again with the origin. And let me use my colors here. So I'm going to have 2 vectors now. So you can think of points as vectors, right? So there are some classes I've seen where they make a big distinction. A point is one thing and a vector is different, but you know they're really containing the same information. They both contain some coordinates, right? So they're these 2 vectors A and B, right? So this has equals to B1, B2 are its coordinates, and this is equal to A1, A2, right? So what I want to measure is something to do with the angle between these vectors. Okay? And And so how do I define the cosine of this angle between A and B? Do I know how to write this in vector notation?
Yes. A dot B.
Yeah, so this is going to be is A dot B. Right?
Divide.
Well, this isn't quite right.
Yes, divide by the lengths of A and B.
Divided by the length of A, the length of A, and the length of B. Yeah, and by length, I mean the two norm, right? The length of the vector is this, right? So, and this is equal to right, so what this is measuring is 1 minus the cosine between the angles of these two vectors. Okay. So first question is this distance symmetric? Was that a yes?
Yes.
Yeah? All right, so who thinks the distance is a metric? Who thinks the distance is not a metric? And who didn't raise their hand? Okay. So let's try this again. All right, so has to be always greater than 0. Cosine is always between cosine is always between minus 1 and 1, right? But because the angle can only be between, I'm looking at the closest angle between them. So I'm not taking the angle that goes all the way around. If I took this angle, it might end up being negative cosine of that angle, right? But I'm always taking the smallest angle, so it's not this. So it's always going to be between 0 and 1. So this property that's greater than 0 is going to be fine. It's this symmetry property. There's everything about this is symmetric with A and B, right? So this is going to be fine.
Can still be less than 0 for angles greater than greater than 90. Cos theta is
Cosine of anything plus pi is cosine of that.
so for angles greater than 90 degrees.
Cosine is always smaller than 1, or at least 1, so you want to minus one thing that is always smaller than 1, so it's always positive.
So what's telling is even if you take the bigger angle, it doesn't make a difference.
Yeah. So, so the distance between these is it's always going to be less than 90. Wait.
So for angle say 120 degrees, it's going to be negative.
So what if I have a vector out here, C? And I want to look at this angle here. Say it's 120 degrees. And what is
120 is less than 0.
Yeah, so it's going to be less than 0. So this is
So 1 minus.
This is minus 1 minus, and then which is 1 positive. So it's,
So then the distance will be larger than 1, right? So it's still okay. The only time that the distance is 0 is if these are pointing along the same direction, right? Okay, so the triangle inequality, what's a way of thinking of the triangle inequality? Well, this is a little trickier. Okay, so let's, after this discussion, so now let's vote again, and this time I want everyone to vote. No more not raising your hand for the third option, or even not even raising the hand for that third option. So, okay, so who thinks the cosine distance is a metric? And who thinks it's not a metric? Okay. Okay, for those who think it's not a metric, does it satisfy the triangle inequality? Okay, so let's just vote of the people who thinks it's not a metric. Which ones of you were just guessing? Okay, so other people who weren't just guessing, who said it didn't violate the triangle inequality? Alright, so no one's, so I guess everyone was guessing, or they thought something
we have
else.
other violations.
There's a different issue. What's the other issue?
The other violation is when A and B are same, it's not 0, it's 1.
Good, okay, so why is that the case?
Because cos of 0 degree is 1.
So cosine of,
So if we have same two vectors, then the angle is 0 and cos
Right.
0 is 1.
So that's a good thing, right?
so cos 0 is 1, and that means the distance is 0. Okay, but why is this a problem?
Distance, if A and B are same, the distance needs to be 0, right?
So A and B
Right.
is different. Yeah.
So if and only if.
A and B is not the same, they could be 0. Again.
Yeah, okay, so what's going on there?
I didn't.
Then they are just.
A and B should be different.
The cosine of
A
A
is not
is
equal
equal
to
to
B.
1.
If they are the same points,
Which is their.
the angle is 0.
Yeah, A and B are not the same.
They're orthogonal,
In
then
case
the
they are.
distance will be equal to
That's
1,
the condition.
right? Because
They can't
cosine.
be- A is not equal.
Okay, so let's draw this. So
That's the condition for cosine.
this is
So that's
For
condition
this
for metric.
this is cosine minus 1, and this is the angle. It starts at 1 and it goes down like this. So this is cosine, then 1 minus cosine is going to start at 0 and go up to 2. And the angle is never greater than pi. The shortest angle is always between pi. So this goes between 0 and 2 of 1 minus cosine of theta.
I'm sorry, I was thinking, I was not taking 1 minus into account. Just thinking
Okay.
cos theta.
Okay, but you're onto something. No, so the issue, so actually it satisfies the triangle inequality, so all that's good. And I'll explain that in a second, why that's true. But the problem here is part 2, that they're equal to 0 if and only if the inputs are the same. Okay? So if they are the same, if A and B are the same, the distance is going to be 0, right? It's 1 minus the cosine, the angle is going to be 0, cosine of the angle is 1, 1 minus 1 is 0. Okay, all that's going to be fine. So that it's the only, so this is if and only if, the only if part is violated. A and B may be different, but the cosine distance will be 0. How can this happen? No, it's not 180 degrees. It's if they're 180 degrees, the angle is pi, the distance will be 2. Right? Yeah, the length is going to be different. Right? So you have A, B, and C. What if B was the same as A, but it was longer? So this is B prime. Okay? Now the angle between A and B is going to be 0. Right? So now the cosine will be 1 and 1 minus 0. The distance will be 0. But these are not the same. A and B prime are not the same. They're different inputs, but they give a distance of 0. Okay? So it violates property M2. So So why would you want this property? Why would you want this to violate this M2 property, where the distance between A and B could be 0, even though they're different, but they're pointing along the same direction?
You're not measuring distances, you're measuring similarity.
Well, similarities and distances are kind of duals of each other. What what you mean is that you want to say A and B prime are respectively the same. Now this is a choice of distance, this is the modeling choice. Okay, so I'll give you a hint. One place where this is used a lot is in modeling text, not using the shingles, but using the bag of words model. Yeah, well, so it'll actually come up in plagiarism or in finding similar web pages or something like that. But you're thinking now as these vectors, they're really, you could think of them as counts in some really high dimensional space. And maybe you have two web pages with one web page has twice as many words as the other web page, and you're counting how many instances of each word. Now, if they have the same, if web page B has twice as many of each word as web page A, so it's the same web page, but you see all the words twice, you're going to say these are really talking about the same thing. Right? You want to normalize out the length of the document. You only want to care about the distribution of words. Let's say A was a summary of B, something like that. B is a really long document, and A is kind of summarizing on the same topic. It's going to have the same sort of distribution of words, but it's going to be much shorter. So you want to say these are similar based on the distribution of words. So this is very popular using the bag of words model for modeling text. And then you want to kind of normalize out the length. This part right here is the normalizing out of the length part. Okay, so the A dot B is really saying, so the cosine is defined this way, but really you should think of it as the dot product of A and B is defined as the norm of A times the norm of B times the cosine of the angle between A and B. Right, so if you define the dot product, which is kind of the similarity here, then it involves the length of these vectors. But you want to normalize out the length. You want to pretend that they've been normalized. And then that's when if you want to do this, then the cosine distance is useful. So, okay, so hopefully this kind of makes sense of why you want to do this. Now kind of let me explain why it satisfies the triangle inequality. Because we're normalizing the vectors, it means it doesn't matter what the length is. That means we can consider if all the vectors live on this unit sphere. Right? So I'm moving A onto the unit sphere. So B prime gets moved into the same spot. B gets moved here, and C is moved here. And this works in high dimensions. You can have a higher dimensional sphere. And then the cosine distance is modeling the length, the shortest path on the sphere. Okay, so it's, forget if it's, I don't think it's exactly that. Is it exactly that distance? Yeah, so it may exactly be that distance. If not, it's isometric to that distance. And so then, if you're going to take a shortcut, if you could take a shortcut from C to A, think this was a higher dimensional sphere, it would be longer to go through B. That would no longer be the shortest path. Because you've normalized, it's then a metric if your input are vectors that lie on the unit sphere. If you restrict it to that, then it's going to be a metric because it's the shortest path on the unit sphere. So that's kind of the easiest way to think about why it satisfies the triangle inequality. And kind of this is a useful way to think. If it's some space and you have these shortest path, it corresponds with the shortest path properties, then going through any other waypoint, if I were trying to get from A to C and I went through a waypoint B, it's going to be further because my distance is defined as the shortest path, the geodesic distance. Okay, so the cosine distance is used a lot in these bag of words model for text. There's an LSH version of this. So Natin had a question about simpler grids doing this LSH. Actually, how you how you do LSH here is actually you pick a random unit vector again, or it can be a random Gaussian vector, and you take the dot product with your value, and it's either -1 or +1. That's it. So only bins, or if the dot product is positive, you get a +1. The dot product is negative, you get a -1. And this turns out to be a locality preserving hash function. It's a very simple hash function. There's two values, but you can repeat it enough times and it becomes, you can use locality sensitive hashing for it. All right, so this is one variation of using these, it's the same sort of input as these LP distances, but it's a different sort of distance, and it captures different properties. It's normalizing out the length. So a different way of measuring the distance between vectors is what's called the KL divergence. Okay. So the KL divergence is also not going to be a metric, but is going to be a way of thinking about these high-dimensional points. But typically, when you think of this, the cosine kind of is distance doesn't always specify that A and B are of a unit length. But in this case, we're going to define it with A and B, which are going to be again in S d-1. So this is the unit sphere in RD, and this means that for A, we have the property that the sum to D of AI squared is going to be equal to 1, right? So A and B are going to be unit vectors. Oh wait, actually, hold on, this is not true. So it's, so I take this back. Actually, it's not on this, this is usually the L2 sphere. This is not the case. So these are going to be vectors in RD such that this property holds. Okay. Sorry. So such that the sum, and actually this is true, and also AI is greater or equal to 0. So all of the values are greater or equal to 0, and the sum of them is going to be equal to 1. Yeah.
Sorry, I just can't read that, such that A.
So the sum of all of the values AI is equal to 1. Let me erase this and write a pledge. And okay, so that this quantity, right? This quantity of the sum of all the entries is equal to 1. So this means it's actually going to be on this L1 sphere, not on the L2 sphere. Okay. So what does this sort of point represent? What's another way of thinking about this? So here, I kind of was normalizing these so they're on the L2 sphere. Right? And I can think about kind of the distribution of the words in some sense on the page. Where's the fraction of each word used? I was kind of doing that, but this is the L2 sphere. This is actually measuring that then A and B are going to be discrete distributions. So then you can think of that AI is going to be the probability that A is equal to I. Right, so if the sum of all these entries equals to 1 and they're all greater or equal than 0, then this is a probability space. right? So that means that AI describes the probability that some object has the value I. That's how you can think of this. So that's another way of why the L1 distance might make sense here. People use the L2 distance to say the difference between probability distributions as well. Maybe the L1 is a little bit more, makes more sense, but actually you can use this KL divergence instead. And it's meant for these kind of discrete probability distributions. So you could again use this, and this is used in other, this is also used for bag of words model. And if you know of this technique called LDA in natural language processing, it's basically doing some weird stuff that's building a topic model that's minimizing this some form of this KL divergence. Okay. So how is this defined? So the KL divergence is defined as times let me there we go. And so actually this is often written as so this is a double vertical bar. If you're using a divergence, you usually write it like this. Okay. So this is kind of to represent that one thing you should notice is this is not symmetric between A and B. Okay? It's if you did the KL divergence from B to A, this is not going to be equivalent. So this should look something kind of this should look something kind of like entropy, right? So that the entropy of a distribution. You've heard of this concept? It's kind of the amount of the amount of disturbance in the force, right? So it's how far it is away from being easy to describe or to approximate with signal processing. So this is related to entropy.